Hey guys, this is Mrs. Brookshire. We are starting chapter 5 today, which is all about probability. So the first section we're doing is 5.1, and this section deals with randomness, probability, and simulation. This is actually part 1, so we're going to talk about randomness and probability, and then the next section, part 2, will be on simulation. Chance is all around us. You and your friends play rock, paper, scissors, determine who gets the last slice of pizza. A coin toss decides which team gets to receive the ball first in a football game. Many adults regularly play the lottery, hoping to win a big jackpot with a few lucky numbers. The traits that children inherit, like their hair and their eye color, their blood type, their handedness, their dimples, whether they can roll their tongues, are all determined by chance involved in which genes their parents pass along. The mathematics of chance behavior is called probability. Probability is the topic of this chapter. Imagine tossing a coin 10 times. How likely are you to get a run of 3 or more consecutive heads? An airline knows that a certain percent of customers who purchase tickets will not show up for a flight. If the airline overbooks a particular flight, what are the chances that they'll have enough seats for their passengers who show up? A couple plans to have children until they have at least one boy and one girl. How many children should they expect to have? To answer these questions, you need a better understanding of how random behavior operates. Okay? So the first thing we're going to do is we're going to talk about the idea of probability. In football, a coin toss helps to determine which team gets the ball first. Why do the rules of football require a coin toss? Because tossing a coin seems a fair way to decide. What does that mean exactly? The following activity should help shed some light on this question. So you guys, we have an activity here. I'm not sure if you guys will end up doing this in class or not, but it's just tossing a coin and recording heads or tails, okay? So you record it and then you tell what proportion. So we all know that the probability of tossing a coin and getting heads is 0.5. So what we're going to do is we are going to go to technology. This would just be tossing it 10 times. So we're going to go to our technology and we're going to do a little coin toss demonstration and see what happens. Okay. So let's see here. Okay. So this is a little applet that's in your book. We all know the probability of heads is 0.5. And so right here, we're going to have the probability of heads, and down here, we're going to have the probability of tails. So we're going to reset this thing, and we're going to just start off with 10 tosses, and we're going to see what happens. And this is going to be your proportion of heads. Now, you would expect it to be 0.5, correct? All right, well, let's see what happens. So we're going to toss it 10 times. Here we go. So we're tossing, and this is the proportion of heads that we get with 10 tosses. Oh, so we did get 0.5 and 0.5. I'm going to tell you that's pretty unusual, okay? I'm going to reset it and do it again. Most of the time, believe it or not, if you only toss 10 coins, you're not going to get that. So that was just a lucky one. All right, let's redo this. So we're going to reset it, and let's do it again. I bet we don't get the same outcome. Okay. So this is kind of normally what happens. So like when you did your first toss and then, this is as you go along, like what your proportion of heads were. So our heads were 0.4 and our tails were 0.6. So this is pretty common. You're not going to get, every time you toss 10 coins, exactly half of them heads, okay? So let's see what happens if we increase this to, let's say, 50. All right, so we're going to reset it and try it again. I think the graph is kind of interesting because if you look at it, what's happening is we're expecting it to be at 50%. So if we drew that line here, you can see that it's kind of like an up and down thing. But what happens is you notice as you get further along is it normally gets closer to 50. So the proportion of heads was 0.52, tails was 0.48. All right, now let's go on and increase it to 200 and reset it and see what happens. So if you look at the graph, it's fluctuating here, and then look what eventually happens. It's getting right there around 0.5. So this is 0.48 and this is 0.52. So this is just kind of illustrating, what probability is, and we're going to go through the definition of that right now. So let's take a look and see. We're going to look at our notes. So we went through here and we did this little applet example over here. And this one was 10 tosses. And that's kind of what happened here. But what we saw is the more we did, the closer it got to fluctuating actually around the 50 or 0.5. Okay. All right. So we got a couple of definitions we're going to discuss. The first one is what is random process and what is probability. Okay. A random process generates outcomes that are determined purely by chance. The probability of any outcome of a random process is a number between 0 and 1 that describes the proportion of times the outcomes would occur in a very long series of trials. Okay, so that's kind of explaining what random process is. It's just a way to generate outcomes determined purely by chance. And then the probability is between 0 and 1, and it describes the proportion that the outcome would occur in a very long series of trials. That's kind of an important statement here, in a very long series of trials. That's what probability is. That's how probability comes about. It's over, you have lots and lots and lots and lots and lots of samples or trials, and whatever happens, you know, with the larger samples is how you come up with your probability. All right, let's talk about the probability being between 0 and 1. Okay, if you look outside today and it's raining, and I say to you, hey, what's the probability that it's raining? You would say it's 1. So anytime probability is certain to happen, it's 1. Okay, I mean, there's no way it's not happening. It's 1. Okay. If I look outside and it's sunny today and I say, hey, what's the probability that it's raining right now? You would say 0 because it's not happening. So probability is always between 0 and 1. 0 is it's not happening or not going to happen, and 1 is it's for sure going to happen. Okay? All right. The law of large numbers is the next definition I want you to write down. So the law of large numbers says that if we observe more and more trials of any random process, the proportion of times that a specific outcome occurs approaches its probability. That's kind of what we saw happening in the coin toss, okay? You know, except for that very first lucky outcome. For the most part, you know, the more coin tosses we do, the closer it's going to get to the true probability. And the true probability of heads is half or 0.5. So that's called the law of large numbers. Okay? All right. A random process is unpredictable in the short run, but has a regular and predictable pattern in the long run. This is the basis for the idea of probability. So short run means not very many samples or not very many trials. But the more trials and samples that you do, the more trials that you perform in the long run, okay, it gets closer and closer and more predictable, a more predictable pattern. So that's kind of what happened here is it started kind of fluctuating around the 0.5. And that's the basis for the idea of probability. All right. Outcomes that never occur have a probability of 0. An outcome that happens half the time in a very long series of trials has a probability of 0.5. And that's what we had happening when we were tossing the coins. Okay, so the probability of heads was 0.5. All right, so now we're going to do a couple of examples. Now, part 2 is going to deal with simulation. So that's another part of probability. So part 2 is simulation. Okay, so let's go over these 2 examples. According to the Book of Odds, the probability that a randomly selected U.S. adult drinks coffee on a given day is 0.56. A, interpret this probability as a long-run relative frequency. And part B, if a researcher randomly selects 100 U.S. adults, will exactly 56 of them drink coffee that day? Explain your answer. All right, so we're going to go through and we're going to answer these. So, part A, when they ask you to interpret this probability on a long run relative frequency, you would say if you take a very large random sample, if you take a very large random sample of US adults, about 56% of them will drink coffee that day. Will drink coffee that day. Okay? So that is interpreting the probability as a long run relative frequency. You want to say you're taking a very large random sample of US adults. About 56% of them will drink coffee that day. About, not exactly, but about. Okay, part B. If a researcher randomly selects 100 US adults, will exactly 56 of them drink coffee that day? Probably not. Okay. Do you think that 100 US adults is a very large random sample? I would have to say no on that. Okay. So with only 100 randomly selected adults, the number who drink coffee that day may not be very close to 56. The number who drink coffee that day may not be close to 56. Okay, and the reason is 100 is really not a very large sample. Sorry, there is a shadow. Let me see if I can get rid of that shadow. Okay, all right, so let's do one more example. Pedro drives the same route to work on Monday through Friday. His route includes one traffic light. According to the local traffic department, there is a 55% probability that the light will be red when Pedro reaches the light. Interpret the probability. Okay. So anytime they ask you to interpret probability, you want to say you're taking a very large random sample, or for this one, yeah, we're doing, let's see, if you take a very large random sample of Pedro's commutes, if you take a very large random sample of Pedro's commutes, about 55% of the time, the light will be red. Okay, so if you take a very large random sample of Pedro's commutes, about 55% of the time, the light will be red. So that is how we would interpret that probability. Okay, number 2, it says probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow with each statement. Be prepared to defend your answer. Okay, so here's some probabilities. Read A, B, C, D. So we're going to write A, B, C, D. Okay, stop this for just a second and read through there and write down which probability you think goes with which statement. Okay, A. This outcome is impossible. It can never occur. You should have put 0. This outcome is certain. It will occur on every trial. That's a 1. This outcome is very unlikely, but it will occur once in a while in a series of trials. So very unlikely to me would be 0.001. Like, don't pick 0.3. That's like 30%. That's not very unlikely. It's somewhat unlikely. I don't even know if you'd say 30% is somewhat unlikely. Okay. All right. This outcome will occur more often than not. Hopefully you put a 0.6 for that one. Okay. Number 3, last question. A husband and wife decided to have children until they have at least one child of each sex. The couple has 7 girls in a row. Their doctor assures them that they are much likely to have a boy next. Explain why the doctor is wrong. Well, why is the doctor wrong? The doctor's wrong because the sex of a baby is a random phenomenon that is unpredictable in the short run. Even though in this long run the probability is close to like 50% male, 50% female, even after a couple has 7 girls in a row, the probability that the 8th child being a boy is 50%. So that's why he's wrong. Okay, so let's kind of write out what we just said. So, the doctor is wrong because the sex of the baby is a random phenomenon. Because the sex of the baby is a random phenomenon that is unpredictable in the short run. Okay, even after a couple has 7 girls in a row, the probability of the 8th child being a boy is still 50%. Even after a couple has 7 girls in a row, poor parents. Got to pay for those girls' weddings. Poor. Even after a couple has 7 girls in a row, the probability of the 8th child being really a girl or a boy, a girl 50%, a boy 50%. Okay. Really, it's just, it has nothing to do with the previous, what's happened in the past. Okay. So you'll hear people say that, oh my gosh, you've already had 3 girls, you should have one more. Yeah, for sure, it's got to be a boy, but that's not true. Okay. That is probability. First section, 5.1, part 1. So the next section is going to be 5.2, and it's going to be all about simulation.